Welcome, students. Today we are going to tackle important short answer questions from past papers on the topic of buoyancy and flotation. This is a crucial part of fluid mechanics. We will break down each question, understand the core physics principles behind it, and then formulate a perfect answer for your exams. The questions cover buoyant force, why ships behave differently in river and seawater, why some objects sink in one liquid but float in another, and the classic question of why ice floats. Let's get started. Let's begin with our first question. This one is from the year 2054. It asks, lead has a greater density than iron and both are denser than water. Is the buoyant force on a lead object greater than, less than, or equal to the buoyant force on an iron object of the same volume? To answer this, we need to recall the fundamental principle governing buoyant force, Archimedes' principle. This principle states that the buoyant force on an object submerged in a fluid is equal to the weight of the fluid displaced by the object. The formula for this is F subscript B equals rho subscript fluid times V subscript displaced times G. Here F subscript B is the buoyant force, rho subscript fluid is the density of the fluid, not the object, V subscript displaced is the volume of the fluid that the object pushes aside, and G is the acceleration due to gravity. The key thing to notice here is that the buoyant force depends on the fluid's density and the displaced volume, not the object's density, mass, or weight. Now let's apply this concept to our question. We are given two objects, one made of lead and one of iron. We are told they have the same volume. Since both lead and iron are denser than water, both objects will sink completely when placed in water. When an object is fully submerged, the volume of fluid it displaces is exactly equal to its own volume. So, since the lead and iron objects have the same volume, they will both displace the exact same volume of water. The buoyant force formula is F subscript B equals rho subscript fluid times V subscript displaced times G. In this case, both objects are in the same fluid, water, so rho subscript fluid is the same for both. And as we just established, V subscript displaced is also the same for both. Of course, G is a constant. Therefore, all the terms on the right side of the equation are identical for both the lead and iron objects, meaning the buoyant force on both must be equal. So, for your exam answer, you should state it clearly. The buoyant force on the lead object is equal to the buoyant force on the iron object. The reasoning is that according to Archimedes' principle, the buoyant force depends on the volume of the displaced fluid. Since both objects have the same volume and are fully submerged in the same fluid, they displace an equal volume of water, resulting in an equal buoyant force. The object's own densities do not affect the buoyant force. Excellent. Now let's move on to our second question from the year 2053. The question is, does a ship sink more in river water or in seawater? Explain. This is a very practical and common question that tests your understanding of flotation. The key concept here is the principle of flotation. This principle is a special case of Archimedes' principle. It states that a floating object displaces a weight of fluid equal to its own weight. So, for any floating object, like our ship, the buoyant force acting on it must exactly balance its total weight. We can write this as F subscript B equals W subscript ship. We also know that F subscript B equals rho subscript fluid times V subscript submerged times G. Notice I'm using V subscript submerged here because the ship isn't fully underwater. Combining these we get rho subscript fluid times V subscript submerged times G equals the weight of the ship. The crucial insight is that the ship's weight is constant, whether it's in a river or the sea. Now we apply this to the two types of water. What's the main difference between seawater and river water? Density. Seawater contains dissolved salts, which makes it denser than fresh river water. Typically, the density of seawater is about 25 kilograms per cubic meter, while for river water it's about 1,000. Let's look at our equation again. Rho subscript fluid times V subscript submerged equals a constant, which is the ship's weight divided by G. This is an inverse relationship. If the fluid density, rho subscript fluid, goes up, then the submerged volume, V subscript submerged, must go down to keep the product constant. Since seawater is denser than river water, the ship needs to displace a smaller volume of seawater to produce the same buoyant force needed to support its weight. A smaller submerged volume means the ship floats higher and sinks less. So the final answer is, a ship sinks more in river water. For the explanation, you should state that seawater is denser than river water due to dissolved salts. According to the principle of flotation, a ship floats by displacing a weight of water equal to its own weight. To displace this fixed weight, the ship needs to submerge a smaller volume in the denser seawater compared to the less dense river water. Therefore, it floats higher in seawater and sinks deeper in river water. All right, let's proceed to the third question from the year 2052. This one asks, steel balls sink in water, but they don't sink in mercury. Why? This question requires a direct comparison of densities between the object and the fluids. The core concept here is the condition for an object to sink or float when fully submerged. An object will sink in a fluid if its average density is greater than the density of the fluid. Why? Because if the object's density is higher, its weight will be greater than the maximum possible buoyant force, which occurs when the object is fully submerged. The weight is rho object times V times G, and the maximum buoyant force is rho fluid times V times G. If rho object is greater than rho fluid, then weight is greater than the buoyant force, and the object sinks. Conversely, if an object's density is less than the fluid's density, it will float. To explain the behavior of the steel ball, we just need to compare the densities. The average density of steel is approximately 750 kilograms per cubic meter. The density of water is about 1,000 kilograms per cubic meter. And the density of mercury is very high, at about 13,600 kilograms per cubic meter. First, let's compare steel and water. Since the density of steel, 780, is much greater than the density of water, 1,000, the steel ball sinks in water. Now, let's compare steel and mercury. The density of steel, 780, is significantly less than the density of mercury, 13,600. Because the steel ball is less dense than the fluid it's in, it will float in mercury. It's as simple as comparing these three values. Your exam answer should be direct and based on this comparison. State that an object sinks in a fluid if its density is greater than the fluid's density, and floats if its density is less. A steel ball sinks in water because the density of steel, around 750 kilograms per cubic meter, is greater than the density of water, 1,000 kilograms per cubic meter. Conversely, the steel ball floats in mercury because its density is less than the density of mercury, around 13,600 kilograms per cubic meter. Finally, we come to our fourth and last question from the year 2050. It's a classic, why does ice float in water? This question seems simple, but it touches on a very unique and important property of water. Just like the last question, the core concept is the condition for floating. An object floats if its density is less than the density of the fluid. So, for ice to float in water, the density of ice must be less than the density of liquid water. This is unusual. For most substances, the solid form is denser than the liquid form. Water, however, exhibits something called anomalous expansion. As liquid water cools, it contracts and becomes denser until it reaches 4 degrees Celsius. Below 4 degrees, as it cools further to become ice at 0 degrees, it starts to expand. This expansion is due to the hydrogen bonds forming a rigid, open crystalline lattice structure, which takes up more space than the more randomly arranged molecules in liquid water. Because of this anomalous expansion, solid water, which we call ice, is actually less dense than liquid water. The density of ice is approximately 917 kilograms per cubic meter, whereas the density of liquid water at the freezing point is closer to 1,000 kilograms per cubic meter. Since the condition for floating, which is rho object less than rho fluid, is met, ice floats on water. This is a crucial property for life on Earth, as it means lakes and rivers freeze from the top down, insulating the water below and allowing aquatic life to survive the winter. If ice were denser than water, it would sink, and bodies of water would freeze solid from the bottom up. For a concise exam answer, you should write, ice floats in water because it is less dense than liquid water. This is due to the anomalous expansion of water. As water freezes, its molecules arrange into a crystalline lattice structure that occupies more volume than in the liquid state. This increase in volume for the same mass results in a lower density, causing the ice to float according to the principle of flotation. So, let's quickly recap what we've learned. All 4 questions revolved around Archimedes' principle and the conditions for flotation. First, we saw that buoyant force depends on displaced volume, not the object's own density. Second, for a floating object like a ship, the density of the fluid determines how much it needs to sink to balance its weight. Third, an object sinks or floats based on a simple comparison between its density and the fluid's density. And finally, the unique property of water's anomalous expansion makes ice less dense, allowing it to float. Understanding these core ideas will help you solve any problem related to buoyancy. Thank you for watching. Hello students! In this video, we'll be tackling a classic problem on buoyancy and forces from the year 2054, question number 5, or. This question is for 3 marks. The question reads, a string supports a solid iron object of mass 180 grams, totally immersed in a liquid of density 800 kilograms per cubic meter. The density of iron is 8,000 kilograms per cubic meter. Calculate the tension in the string. Let's break this down step by step. First, let's list down all the information the problem gives us. This is always a good practice. We are given the mass of the iron object, let's call it m, which is 180 grams. Remember, we must always work in SI units, so we'll convert this to kilograms by dividing by 1,000. So m equals 0. 18 kilograms. Next, the density of the liquid, which we'll denote as ρL, is 800 kilograms per cubic meter. The density of iron, ρI, is 8,000 kilograms per cubic meter. We also need the acceleration due to gravity, g, which we'll take as 10 meters per second squared for this calculation. Now, let's understand the physics concept involved. When the iron object is hanging in the liquid, there are 3 forces acting on it. First, its own weight, W, acts vertically downwards. Second, the liquid exerts an upward buoyant force, or upthrust, U, on the object. This is due to Archimedes' principle. And third, the string is pulling the object upwards with a tension force, T. Since the object is stationary, it's in equilibrium. This means all the upward forces must exactly balance the downward force. So, the tension plus the upthrust must equal the weight of the object. Based on our understanding of the forces in equilibrium, we can write down our main formula. The total upward force equals the total downward force. So T plus U equals W. Our goal is to find the tension, T. By rearranging this equation, we get the formula for tension, T equals W minus U. So, to find the tension, we need to calculate the true weight of the object and subtract the upthrust acting on it. This value T is also sometimes called the apparent weight of the object in the liquid. Let's start substituting our values into the formulas for weight and upthrust. First, the weight W is simply mass times gravity. So, W equals 0. 18 kilograms times 10 meters per second squared. Next, the upthrust, U. The formula for upthrust is the volume of the displaced liquid times the density of the liquid times gravity. Since the object is totally immersed, the volume of displaced liquid is equal to the volume of the iron object itself. We don't have the volume directly, but we can calculate it using the formula, volume equals mass divided by density. So the volume of the iron, V, equals 0. 18 kilograms divided by 8,000 kilograms per cubic meter. Now, let's do the arithmetic. First, for the weight, W equals 0. 18 times 10, which gives us 1.8 newtons. Now for the upthrust. We first need the volume. V equals 0. 18 divided by 8,000, which is 0. 0.00025 cubic meters. Now we can calculate the upthrust, U. U equals this volume, 0.00225, multiplied by the liquid's density, 800, and then by gravity, 10. This gives us an upthrust of 0.18 newtons. Finally, we find the tension, T equals W minus U, which is 1.8 minus 0.18. After performing the final subtraction, 1.8 minus 0.18, we get our final answer. The tension in the string is 1.62 newtons. It's important to always include the correct units in your final answer, which in this case is newtons, the unit of force. So, the final calculated tension in the string is 1.62 newtons. This matches the expected answer. To summarize, we solved this problem by applying the principle of equilibrium. We identified the three forces acting on the submerged object, its weight, the upthrust, and the tension. By setting the upward forces equal to the downward force, we derived the equation T equals W minus U. We then calculated the weight and the upthrust separately, using the given mass and densities, and subtracted them to find the final tension in the string. A straightforward application of force balance and Archimedes' principle. Hello students! Welcome to our solution session. Today, we're tackling a numerical problem from the 2073 supplementary exam. It's question number 11 and is worth 2 marks. The question reads, a boy can lift a maximum load of 250 N of water. How many liters of mercury of density 13,600 kilograms per cubic meter can he lift in an identical vessel? First, let's identify and list down all the information given in the problem. The maximum load the boy can lift is given as the weight of water he can carry. So, the maximum weight, which we'll call W, is 250 newtons. We are also given the density of mercury, which is 13,600 kilograms per cubic meter. The question asks for the volume of mercury in liters. For our calculations, we will use the acceleration due to gravity, g, as 10 meters per second squared, which simplifies the math. Now, let's think about the physics concept behind this question. The problem states that the boy can lift a maximum load of 250 newtons. This tells us the maximum force or weight that his muscles can support. This lifting capacity is constant. It doesn't matter whether he is lifting water or mercury. The maximum weight he can lift remains the same, which is 250 newtons. The phrase in an identical vessel simply implies a comparable lifting situation. The core idea is that the weight of the mercury he can lift must be equal to the maximum load he can handle. Our task is to find what volume of mercury has this weight. To solve this, we need the relationship between weight, density, and volume. We know that weight W is equal to mass, m, times the acceleration due to gravity, g. So W equals m times g. We also know that density, ρ, is mass per unit volume. This means mass, m, equals ρ times volume, v. By substituting the expression for mass into the weight equation, we get our main formula, weight W equals density, ρ, times volume, v, times acceleration due to gravity, g. We want to find the volume of the mercury, so let's rearrange our formula to solve for v. By dividing both sides by ρ times g, we get that volume, v, equals weight, W, divided by the product of density, ρ, and gravity, g. Now we can substitute the values we listed earlier. The weight, W, is 250 newtons. The density of mercury, ρ, is 13,600 kilograms per cubic meter. And we're using g as 10 meters per second squared. So, the volume of mercury, V, equals 250 divided by the quantity, 13,600 multiplied by 10. Let's perform the calculation. First, we'll evaluate the denominator. 13,600 times 10 gives us 186 joules. So, our equation becomes V equals 250 divided by 186 joules. Performing this division, we get a volume of approximately 0.001838. Since we used standard C units for weight, density, and gravity, our resulting volume is in the standard unit for volume, which is cubic meters. We are almost done, but the question specifically asks for the answer in liters, not cubic meters. So, we need to convert our result. The key conversion factor to remember is that 1 cubic meter is equal to 1,000 liters. To convert from cubic meters to liters, we simply multiply our result by 1,000. So, 0.00138 cubic meters multiplied by 1,000 gives us 138 liters. Therefore, the buoy can lift 138 liters of mercury. To quickly summarize, the key to this problem was realizing the buoy's maximum lifting capacity is a constant weight, given as 250 newtons. We then use the fundamental relationship between weight, density, and volume, W equals rho times V times G, to find the volume of mercury that corresponds to this maximum weight. A final unit conversion from cubic meters to liters gave us our answer. Thank you for watching. Hello students. Let's solve a classic problem on buoyancy from the 2066 Old Q. No. 3B paper. The question is, a geologist finds that a moon rock whose mass is 7.2 kilograms has an apparent mass of 5.88 kilograms when submerged in water. What is the density of the rock? This question tests our understanding of Archimedes' principle, and it's worth 4 marks, so let's get it right. First, let's list our known values. The real mass of the rock, which we'll call m, is 7.2 kilograms. Its apparent mass in water, which we'll call mAp, is 5.88 kilograms. The fluid is water, so we'll use its standard density, rho water, which is 1,000 kilograms per cubic meter. Our goal is to find the density of the rock, rho rock. It's always a good practice to write these down before you start. The key concept here is Archimedes' principle. When an object is submerged in a fluid, it experiences an upward buoyant force. This force makes the object seem lighter. The principle states that this buoyant force is equal to the weight of the fluid the object displaces. So, the difference between the rock's real weight and its apparent weight is exactly this buoyant force. From the loss in mass, we can determine the mass of the displaced water. And since we know water's density, we can then find the volume of the displaced water, which is equal to the volume of the rock itself. This is the crucial link we need to find the rock's density. Let's set up our formulas. The density of the rock, rho rock, is its mass divided by its volume, m over v rock. From Archimedes' principle, the loss in mass m minus mAp equals the mass of the displaced water. This mass is the volume of the rock times the density of water. So, v rock equals m minus mAp divided by rho water. Combining these, we get our main working formula, rho rock equals m times rho water, all divided by m minus mAp. Now we'll substitute our values into this formula. The formula is, density of the rock equals real mass times density of water divided by the difference between real mass and apparent mass. So rho rock equals 7.2 multiplied by 1,000, and this entire product is divided by the quantity 7.2 minus 5.88. Let's write that out clearly. In the numerator, we have 7.2 times 1,000. In the denominator, we have the subtraction 7.2 minus 5.88. Taking it one step at a time is the best way to avoid mistakes. Let's perform the calculation. The numerator is simple, 7.2 multiplied by 1,000 equals 7,200. For the denominator, we need to subtract 5.88 from 7.2. The result of this subtraction is 1.32. So, our equation now is rho rock equals 7,200 divided by 1.32. Using a calculator for this division, we get 5,454. 5,454 repeating. This is our numerical result before we consider rounding in units. For our final answer, we'll round the result to 2 decimal places. This gives us 5,454. 54. It's very important to include the correct units. Since our mass was in kilograms and we calculated volume in cubic meters, the density is in kilograms per cubic meter. So, the final answer is, the density of the rock is 5.54 kilograms per cubic meter. To summarize, we used Archimedes' principle to solve this problem. We found the rock's volume by calculating the loss in mass when it was submerged in water. Once we had the volume and the given mass, we used the fundamental formula for density, which is mass divided by volume, to arrive at our final answer. It's a straightforward application of a very important principle in fluid mechanics. Hello students. Welcome. In this video, we'll be solving a numerical problem from the 2065 board exam, question number 3B. This question is worth 3 marks and deals with forces on a submerged object. The question asks, a string supports a solid iron object of mass 200 grams, totally immersed in a liquid of specific gravity 0. 9. Calculate the tension in the string if the density of iron is 8,000 kilograms per cubic meter. Let's break it down together. First, let's list down all the information the problem gives us. The mass of the iron object, which we'll call m, is 200 grams. We must convert this to SI units, so that's 0. 2 kilograms. The specific gravity of the liquid is 0. 9. The density of iron, let's call it ρ iron, is 8,000 kilograms per cubic meter. We'll also use the standard density of water, which is 1,000 kilograms per cubic meter, and for this problem, we'll use g, the acceleration due to gravity, as 10 meters per second squared to simplify the calculation. Now, let's understand the physics at play here. When the iron object is hanging in the liquid, it's in a state of equilibrium. This means all the forces acting on it are balanced. There are 3 main forces. First, the object's weight, W, acts downwards due to gravity. Second, the liquid exerts an upward buoyant force, or upthrust, U, on the object, as described by Archimedes' principle. Third, the string is pulling the object up with a tension force, T. Since the object is stationary, the total upward forces must equal the total downward force. So, the tension plus the upthrust must be equal to the weight. From our understanding of the forces, we can set up our main equation. The upward forces, tension plus upthrust, equal the downward force, weight. So T plus U equals W. To find the tension, we can rearrange this formula to T equals W minus U. This tells us that the tension in the string is the object's actual weight minus the buoyant force acting on it. To solve this, we need to calculate W and U separately. The formula for weight, W, is mass times g. The formula for upthrust, U, is the volume of the displaced liquid times the density of the liquid times g. Let's begin substituting our values. First, let's find the weight, W. W equals mass times g, which is 0. 2 kilograms multiplied by 10 meters per second squared. Next, we'll work towards finding the upthrust, U. The formula for upthrust needs the volume of the object and the density of the liquid. The volume of the iron object is its mass divided by its density. So V equals 0. 2 kilograms divided by 8,000 kilograms per cubic meter. The density of the liquid is its specific gravity times the density of water, which is 0. 9 multiplied by 1,000 kilograms per cubic meter. Now we have all the pieces to find the upthrust. Let's do the arithmetic now. The weight W is 0. 2 times 10, which gives us 2 newtons. The volume of the iron, V, is 0. 2 divided by 8,000, which equals 0. 0.00025 cubic meters. The density of the liquid is 0. 9 times 1,000, which is 900 kilograms per cubic meter. Now we can calculate the upthrust, U. It's volume times liquid density times g. So, U equals 0. 0.00025 times 900 times 10. This calculates to 0. 25 newtons. Finally, we find the tension, T equals W minus U, which is 2 newtons minus 0. 25 newtons. Completing the final subtraction, 2 minus 0. 25 gives us 1. 775. So, the tension in the string is 1.775 newtons. This is our final answer. It's very important to write the unit, newtons, after the numerical value to get full marks. The tension is less than the object's actual weight because the buoyant force from the liquid is helping to support the object. So, to quickly summarize our solution, we first identified the three forces in equilibrium: weight acting down, and tension and upthrust acting up. From the equilibrium condition, we derived our main formula: tension equals weight minus upthrust. We then calculated the weight of the object and the upthrust from the liquid separately, and finally subtracted them to find the tension. Remember this method for any problem involving objects submerged in fluids. Hello, Class 12. Today, we're tackling a numerical problem from the 2064 question paper, question number 3B. It's a 3-mark question about alloys and density. Let's read it together. An alloy of mass 588 grams and volume 1,000 cubic centimeters is made of iron and aluminum. The density of iron is 8.0 grams per cubic centimeter and aluminum is 2.7 grams per cubic centimeter. We need to calculate the proportion by volume and by mass of the constituents. First, let's list down all the information the problem gives us. This is always the best first step. The total mass of the alloy, let's call it M, is 588 grams. The total volume of the alloy, V, is 1,000 cubic centimeters. The density of the first component, iron, which we'll call rho iron, is 8.0 grams per cubic centimeter. And the density of the second component, aluminum or rho aluminum, is 2.7 grams per cubic centimeter. All the units are in the gram-centimeter system, so we can work with them for now and convert to standard C units at the end. The key concept here is that an alloy is a simple mixture. This means two basic principles apply. First, the total mass of the alloy is simply the sum of the masses of its parts. So, the mass of the iron plus the mass of the aluminum equals the total mass of the alloy. Second, we assume that the volumes are also additive. The volume of the iron plus the volume of the aluminum will equal the total volume of the alloy. Using these two simple conservation ideas, we can set up two separate equations to solve for our two unknowns, the mass and volume of each component. To connect our two equations for mass and volume, we need the fundamental formula for density. Remember, density is defined as mass per unit volume. So, rho equals m divided by v. We can rearrange this to find the mass of a substance if we know its density and volume. Mass equals density multiplied by volume, or m equals rho times v. We will use this relationship to express the mass of the iron and aluminum in terms of their volumes, which will help us solve the problem. Now, let's set up our equations. Let Vi be the volume of iron and Va be the volume of aluminum. Our first equation from the total volume is Vi plus Va equals 1,000. Our second equation from the total mass is Mi plus Ma equals 588. Using our formula, this becomes rho I times Vi plus rho A times Va equals 588. Now, before we substitute the density values, let's do a quick check. The average density of this alloy is mass over volume, which is 588 divided by 1,000, or 0.588 grams per cubic centimeter. This is less than the density of both iron and aluminum, which is physically impossible. This indicates a typo in the question. The most likely error is a factor of 10 in the mass. We will assume the mass should be 588 grams to proceed. So our corrected mass equation is 8.0 times Vi plus 2.7 times Va equals 580. We now have a system of two equations. From the volume equation, we can write Va equals 1,000 minus Vi. Let's substitute this into our corrected mass equation. We get 8.0 times Vi plus 2.7 times 1,000 minus Vi equals 580. Expanding this gives 8.0 Vi plus 2,700 minus 2.7 Vi equals 580. Combining the terms with Vi, we get 5.3 Vi. Moving 2,700 to the other side gives 580 minus 2,700, which is 380. So 5.3 3 VI equals 3. Dividing by 5. 3, we find that the volume of iron VI is 600 cubic centimeters. This means the volume of aluminum VA is 1000 minus 600, which is 400 cubic centimeters. So, for part 1, the proportion by volume is 600 cubic centimeters of iron and 400 cubic centimeters of aluminum. To match the expected answer format, we convert to cubic meters. This is 6 times 10 to the power of minus 4 cubic meters for iron and 4 times 10 to the power of minus 4 cubic meters for aluminum. For part 2, the proportion by mass, we use mass equals density times volume. Mass of iron is 8. 0 times 600, which is 4,800 grams, or 8 kilograms. Mass of aluminum is 2. 7 times 400, which is 80 grams, or 1.08 kilograms. Note that the provided answer key states 0. 48 kg and 0. 108 kg, which would be correct if the total volume was 100 cubic centimeters instead of 1000. To summarize, we solved this problem by setting up two simultaneous equations based on the conservation of mass and volume. The key was using the density formula, mass equals rho times volume, to link the two equations. We also encountered an important lesson: always do a quick reality check on the given numbers. Here, the average density was impossible, which pointed to a typo in the question. By correcting it, we were able to find a physically consistent solution. Always be critical and think through the problem logically. Hello students! In this video, we'll be tackling a classic physics problem from the 2062 question paper, question number 3B. This is a 3-mark question. It states, a string supports a solid iron object of mass 200 grams, totally immersed in a liquid of density 800 kilograms per cubic meter. The density of iron is 8,000 kilograms per cubic meter. We need to calculate the tension in the string. Let's break this down step by step. First, let's list down all the information the problem gives us. The mass of the iron object, which we'll call m, is 200 grams. We must convert this to SI units, so that's 0.2 kilograms. The density of the liquid, let's call it rho sub L, is 800 kilograms per cubic meter. The density of the iron object, or rho sub I, is 8,000 kilograms per cubic meter. We're also going to use the acceleration due to gravity, g, which we'll take as 10 meters per second squared for this calculation. The key concept here is Archimedes' principle and forces in equilibrium. When the iron object is submerged in the liquid, 3 main forces are acting on it. First, its own weight acts downwards. Second, the liquid exerts an upward buoyant force, also known as upthrust. And third, the string is pulling it upwards, which is the tension we need to find. Since the object is stationary and supported by the string, these forces are balanced. The total upward force, which is the tension plus the upthrust, must be equal to the total downward force, which is the weight of the object. Based on the concept of equilibrium, we can write our main formula, tension plus upthrust equals weight. We can write this as T plus U equals W. To solve for tension, we rearrange this to T equals W minus U. Now, we need the formulas for weight and upthrust. The weight W is simply mass times gravity, or m times g. The upthrust, U, according to Archimedes' principle, is the weight of the displaced liquid. This is calculated as the volume of the object, V, multiplied by the density of the liquid, rho sub L, multiplied by g. Now let's start substituting our values. First, we need the volume of the iron object. We know that density equals mass over volume, so volume equals mass divided by density. The volume of the iron, V, is its mass, 0.2 kilograms, divided by its density, 8,000 kilograms per cubic meter. This gives us a volume of 0.00025 cubic meters. Now we can calculate the weight, W. It's mass times g, so 0.2 kilograms times 10 meters per second squared, which equals 2 newtons. Next, the upthrust, U, is the volume we just found, multiplied by the liquid's density and g. So it's 0.00025 times 800 times 10. Let's do the arithmetic. We already found the weight is 2 newtons. Now for the upthrust. We are calculating 0.00025 multiplied by 800, which gives us 0.02. Then we multiply that by g, which is 10. So 0.02 times 10 gives us an upthrust of 0.2 newtons. Our main formula is tension equals weight minus upthrust. So the tension is 2 newtons minus 0.2 newtons. This calculation is straightforward. After subtracting the upthrust from the weight, we get our final result. 2 minus 0.2 equals 1.8. Therefore, the tension in the string is 1.8 newtons. This is the final answer to the problem, and it matches the expected answer. Remember to always include the correct units, which in this case is newtons, the SI unit for force. So, to recap, we solved this problem by identifying all the forces acting on the submerged object, its downward weight, and the upward forces of tension and upthrust. We use the formula for upthrust from Archimedes' principle, set up an equilibrium equation where upward forces equal downward forces, and solved for the unknown tension. The key was to first calculate the object's volume to find the upthrust. Hello students, and welcome to our solution series. Today, we're tackling a classic problem from the year 2057, question number 3b. This is a 3-mark question on fluid mechanics. The question reads, a string supports a solid iron of mass 200 grams, totally immersed in a liquid of density 900 kilograms per cubic meter. Calculate the tension in the string if the density of iron is 8,000 kilograms per cubic meter. Let's break this down step by step. First, let's identify and list all the given values from the problem. We are given the mass of the solid iron, which is 200 grams. It's crucial to convert this to C units, so 200 grams becomes 0.2 kilograms. Next, we have the density of the liquid, which is 900 kilograms per cubic meter. And finally, the density of the iron itself is 8,000 kilograms per cubic meter. For our calculations, we will use the value of acceleration due to gravity, g, as 10 meters per second squared. To solve this, we need to understand the forces acting on the iron block. Since the block is hanging from a string and is completely submerged in a liquid, there are 3 main forces at play. First, there's the weight of the iron acting vertically downwards. Second, there's the tension in the string pulling vertically upwards. And third, there's the buoyant force, or upthrust, exerted by the liquid, which also acts vertically upwards. Because the iron block is held stationary, it's in a state of equilibrium. This means the total upward forces must perfectly balance the total downward force. Based on our understanding of the forces, we can set up a simple equation for equilibrium. The total upward force is the sum of the tension and the upthrust. The total downward force is the weight. So our equation is tension plus upthrust equals weight. To find the tension, which is what the question asks for, we can rearrange this formula to be tension equals weight minus upthrust. To use this, we'll need to calculate both the weight of the iron and the upthrust from the liquid. Now let's start substituting our values. We'll calculate the weight and the upthrust separately. First, the weight, which we'll call W. The formula for weight is mass times acceleration due to gravity, or W equals m times g. So W equals 0.2 kilograms multiplied by 10 meters per second squared. Now for the upthrust, U. Archimedes' principle tells us that upthrust is the weight of the liquid displaced. To find this, we first need the volume of the iron, since it's fully submerged. Volume equals mass divided by density. So, the volume of the iron is 0.2 kilograms divided by 8,000 kilograms per cubic meter. Let's do the arithmetic. First, for the weight, W equals 0.2 times 10, which gives us exactly 2 newtons. Next, let's find the volume of the iron, V equals 0.2 divided by 8,000. This comes out to be 0.00025 cubic meters. Now we can calculate the upthrust, U. The formula is volume times the density of the liquid times g. So, U equals 0. 0.00025 times 900 times 10. This calculation gives us an upthrust of 0.25 newtons. We are now ready to find the final answer. Our main formula is tension equals weight minus upthrust. We found the weight to be 2 newtons and the upthrust to be 0.25 newtons. Substituting these values, we get tension equals 2 minus 0.25. This gives us a final result of 1.775 newtons. So, the tension in the string is 1.775 newtons. This is our final answer. Let's quickly recap what we did. We analyzed the forces on an object submerged in a liquid, its weight acting down, and tension and upthrust acting up. By applying the principle of equilibrium, we established that tension equals weight minus upthrust. We calculated the weight using W equals mg and the upthrust using Archimedes' principle, which required us to first find the object's volume. Subtracting the upthrust from the weight gave us the final tension in the string. Hello students! Today, we're going to solve a classic physics problem on flotation from the 2056 question paper. It's question number 3B, and it carries 3 marks. The question reads, an iceberg having a volume of 2060 cc floats in seawater of density 30 kilograms per cubic meter with a portion of 224 cc above the surface. We are asked to calculate the density of ice. First, let's list down all the information that has been given to us. The total volume of the iceberg, let's call it V total, is 2060 cubic centimeters. The density of the seawater, which we'll denote as rho water, is 130 kilograms per cubic meter. And finally, the volume of the iceberg that is visible above the water surface, V above, is 224 cubic centimeters. Our objective is to find the density of the ice, or rho ice. The fundamental physics principle at play here is the law of flotation, which is a direct application of Archimedes' principle. This law states that the weight of a floating object is equal to the weight of the fluid it displaces. In our case, this means the total weight of the iceberg is being supported by the buoyant force from the seawater. This buoyant force is exactly equal to the weight of the water displaced by the submerged part of the iceberg. So, the main idea is, the weight of the entire iceberg equals the weight of the displaced seawater. From this principle, we can develop our working formula. We know that weight equals mass times g, the acceleration due to gravity. And mass is density times volume. So, the weight of the iceberg can be written as density of ice times total volume times g. Similarly, the weight of the displaced water is density of water times the submerged volume times g. By equating these two, we get a simple and powerful relation. The density of ice multiplied by the total volume is equal to the density of water multiplied by the submerged volume. Before we can substitute the values, we need to calculate the submerged volume of the iceberg. We have the total volume and the volume above the surface. So, the submerged volume, or V submerged, is simply the total volume minus the volume above. That is 2060 cc minus 224 cc, which gives us 18 cubic centimeters. Now we have all the pieces. One important note, since we are using a ratio of volumes on both sides of the equation, the units of cubic centimeters will cancel out, so we don't need to convert them to cubic meters. This simplifies our calculation. Now, let's solve for the density of ice. We need to rearrange our equation to isolate rho ice. So, rho ice equals 130 multiplied by 1836, with the entire result divided by 2060. Let's calculate the numerator first. 30 times 1886 is 1,891,080. Now, we divide this number by 2060. So, 1,891,080 divided by 2060 equals exactly 918. Since the density of water was in kilograms per cubic meter, our final unit for the density of ice will also be in kilograms per cubic meter. So, the final answer is that the density of the ice is 918 kilograms per cubic meter. This result is logical because for an object to float, its density must be less than the density of the fluid it's in. In this case, 918 kilograms per cubic meter is indeed less than the 130 kilograms per cubic meter of the seawater. This confirms our answer is reasonable. Make sure to write your final answer clearly with the correct units. To quickly recap, we solved this problem by applying the law of flotation. The key step was to understand that the weight of the entire iceberg is equal to the weight of the displaced seawater. From this, we derived a simple relationship between the densities and volumes. After calculating the submerged volume, we plugged in the numbers and solved for the density of ice. Always remember this core principle for any flotation problem. Hello students! Today, we're tackling a numerical problem from the 2055 question paper. It's question number 6, the or part, and it's worth 3 marks. The question reads, a piece of gold aluminium alloy weighs 100 cc in air and 80 g in water. What is the weight of the gold in the alloy if the relative density of gold is 19? 3, and that of aluminium is 2. 5. Now you might notice a small typo here. 100 cc is a unit of volume, not weight. Given the context, we can confidently assume this was meant to be 100 grams. Let's proceed with that understanding. First, let's list down all the information we've been given. The mass of the alloy in air is 100 grams, which is 0.1 kilograms in C units. The apparent mass of the alloy in water is 80 grams, or 0.08 kilograms. The relative density of gold is 19.3, so its actual density is 19. 3 times 1,000, which is 19,300 kilograms per cubic meter. Similarly, the relative density of aluminium is 2.5, making its density 2,500 kilograms per cubic meter. We also know the density of water, which is 1,000 kilograms per cubic meter. The key concept we need to use here is Archimedes' principle. This principle states that the buoyant force on a submerged object is equal to the weight of the fluid that the object displaces. This buoyant force is what causes the apparent loss in weight when the alloy is placed in water. So, by calculating the loss in mass, we can find the mass of the water displaced. And since we know the density of water, we can then determine the volume of the water displaced, which is exactly equal to the total volume of our alloy piece. Once we have the total volume, we can relate it to the volumes of the gold and aluminium inside. Let's lay out the formulas. First, the loss of mass is the mass in air minus the apparent mass in water. Second, the total volume of the alloy is this loss of mass divided by the density of water. We will also use 2 more equations. Total mass of the alloy equals the mass of gold plus the mass of aluminum. And finally, the total volume of the alloy equals the volume of gold plus the volume of aluminum. Remember, volume can be expressed as mass divided by density. Now, let's substitute our values. First, let's find the total volume of the alloy. The loss of mass is 0.1 kilograms minus 0.08 kilograms, which is 0.02 kilograms. The total volume is this loss of mass, 0.02 kilograms, divided by the density of water, 1,000, giving us 0.0002 cubic meters. Now, let's use our main equations. Let the mass of gold be m subscript g. The total mass is 0.1 kilograms, so the mass of aluminium must be 0.1 minus m subscript g. Substituting these into our volume formula gives us 0.0002 equals m subscript g divided by 19,300 plus 0.1 minus m subscript g divided by 2,500. Let's solve this equation for the mass of gold. We can split the second term on the right-hand side. The equation becomes 0.0002 equals mg divided by 19,300 plus 0.1 divided by 2,500 minus mg divided by 2,500. Now 0.1 divided by 2,500 is 0.0004. Let's move this to the left side. 0.00002 minus 0.0004 gives us negative 0.0002. On the right, we group the mg terms. After some algebraic manipulation and finding a common denominator, we get that negative 0.0002 equals mg times a negative fraction. Solving for mg, we get mg equals approximately 0.05744 kilograms. So, our calculation gives us a mass for gold of about 0.05744 kilograms. Rounding this to a reasonable number of significant figures, we get 0.057 kilograms. The question asks for the weight of the gold, but the expected answer is in kilograms, a unit of mass. In physics problems like this, weight is often used interchangeably with mass. If you needed the true weight, you would multiply this mass by the acceleration due to gravity, g. But for this question, the required answer is the mass. So, the final answer is 0.057 kilograms. To summarize, we solved this problem in two main steps. First, we used Archimedes' principle. We calculated the loss of mass of the alloy in water to find its total volume. Second, we set up two equations, one for the total mass and one for the total volume, both in terms of the mass of gold and the mass of aluminum. By solving these two equations simultaneously, we were able to isolate and find the mass of the gold in the alloy. I hope this explanation was clear. Thank you for watching. Hello students. In this video, we'll be tackling a classic problem on buoyancy and forces from the year 2054, question number 5, or. This question is for 3 marks. The question reads, a string supports a solid iron object of mass 180 grams, totally immersed in a liquid of density 800 kilograms per cubic meter. The density of iron is 8,000 kilograms per cubic meter. Calculate the tension in the string. Let's break this down step by step. First, let's list down all the information the problem gives us. This is always a good practice. We are given the mass of the iron object, let's call it m, which is 180 grams. Remember, we must always work in SI units, so we'll convert this to kilograms by dividing by 1,000. So m equals 0.18 kilograms. Next, the density of the liquid, which we'll denote as ρL, is 800 kilograms per cubic meter. The density of iron, ρI, is 8,000 kilograms per cubic meter. We also need the acceleration due to gravity, g, which we'll take as 10 meters per second squared for this calculation. Now, let's understand the physics concept involved. When the iron object is hanging in the liquid, there are 3 forces acting on it. First, its own weight, W, acts vertically downwards. Second, the liquid exerts an upward buoyant force, or upthrust, U, on the object. This is due to Archimedes' principle. And third, the string is pulling the object upwards with a tension force, T. Since the object is stationary, it's in equilibrium. This means all the upward forces must exactly balance the downward force. So, the tension plus the upthrust must equal the weight of the object. Based on our understanding of the forces in equilibrium, we can write down our main formula. The total upward force equals the total downward force. So T plus U equals W. Our goal is to find the tension, T. By rearranging this equation, we get the formula for tension, T equals W minus U. So, to find the tension, we need to calculate the true weight of the object and subtract the upthrust acting on it. This value T is also sometimes called the apparent weight of the object in the liquid. Let's start substituting our values into the formulas for weight and upthrust. First, the weight W is simply mass times gravity. So, W equals 0.18 kilograms times 10 meters per second squared. Next, the upthrust, U. The formula for upthrust is the volume of the displaced liquid times the density of the liquid times gravity. Since the object is totally immersed, the volume of displaced liquid is equal to the volume of the iron object itself. We don't have the volume directly, but we can calculate it using the formula, volume equals mass divided by density. So the volume of the iron, V, equals 0.18 kilograms divided by 8,000 kilograms per cubic meter. Now, let's do the arithmetic. First, for the weight, W equals 0. 18 times 10, which gives us 8 newtons. Now for the upthrust. We first need the volume. V equals 0. 18 divided by 8,000, which is 0.00025 cubic meters. Now we can calculate the upthrust, U. U equals this volume, 0.0000225, multiplied by the liquid's density, 800, and then by gravity, 10. This gives us an upthrust of 0.18 newtons. Finally, we find the tension, T equals W minus U, which is 8 minus 0.18. After performing the final subtraction, 8 minus 0.18, we get our final answer. The tension in the string is 62 newtons. It's important to always include the correct units in your final answer, which in this case is newtons, the unit of force. So, the final calculated tension in the string is 1.62 newtons. This matches the expected answer. To summarize, we solved this problem by applying the principle of equilibrium. We identified the three forces acting on the submerged object, its weight, the upthrust, and the tension. By setting the upward forces equal to the downward force, we derived the equation T equals W minus U. We then calculated the weight and the upthrust separately, using the given mass and densities, and subtracted them to find the final tension in the string. A straightforward application of force balance and Archimedes' principle.